Okay guys and gals, one last video on shear and moment diagrams. So this problem we have a distributed load and a point load, and so let's look at what the shape and magnitudes of the shear and moment diagrams are in this. So the first thing I'm going to do is calculate the end reactions. It's just kind of a part of life in this analysis. So I'll do that, come back, and then we'll crank out the shear and moment diagrams. Okay folks, so I solved for the end reactions. I first summed moments about S to get Q. I just named them whatever I wanted. Summed moments about Q to get S. And then I summed forces to check that the input loads were equal to the reactions. Again, checking my work. As we saw in the last example, when I made a mistake, it was 2/3 of the way, and it took me a little doing to get that cleaned up. So in the end, checking our work at steps is worthwhile. It saves us rework, saves us just going down the wrong path. Okay, so with that said, I want to draw the shear and moment diagrams for this thing. So to set myself up, I'm going to just crib off of this moment, or this load diagram up here. Let me just write the reactions up here so I can see them easier. Then I'll just throw my calc paper up here and start to work through this. Alright, let me pull this down. Okay, so I'm just going to extend those lines down. Easier on one sheet of paper, but that's okay. Okay, so I'll draw my line for the shear and moment diagrams. Just get this guy set up. Okay, so I'm going to start at the left as I cross the first load, and ideally we would draw this this dimension should come to the center line of the support here. Let me just clean that up. Okay, so as I cross the first reaction at 764.7, that gives me this point on my shear diagram. So vertical goes up, the vertical reaction, so 760, I'm just going to round it off to 765. And then as I apply my distributed line load here, it's going to reduce my shear in a triangular form. So let's calculate it out here so I know the slope of my line. So I'm going to multiply 100 pounds per foot times 10 gives me 1,000 pounds. Subtract it from here, so I have 765 minus 1,000 gives me negative 235 kips of shear. And I'm going to draw this sort of in proportion. I could be more rigorous, but I don't know that I gain much for doing that. Okay. Then between this point and this point I have no loads, so I have no change in shear. So it's just a straight line across here. And then I have a 500 pound load. Now I should write down 500 pound load acting down, so I add that to this guy. So that's going to push me to the minus 735. So to get that, I took 235 pounds of shear, which is where I am here, and added the 500 pound point load to it. So I draw that. And then I have nothing until I get to the end here. So I'm horizontal. And then I get to the end and I have 735.3. Again, I rounded a little bit, so I have 735 here, 735 there, and I am grateful that my shear diagram closes and I have zero shear once I get to the right hand side of that reaction. Okay, so that's the first part. The second part of this is to calculate the moment diagram, and to do that I'm going to be interested in this point here. I'll call that X. I have that point defined, that point is defined in that. So the only dimensional variable I don't have is X. And X is going to be 765. So we're going to set X. Sorry, I'm making this confusing. So what I need to do to find X is to find out when this distributed load equals the reaction here, or the shear at the end. So to write that out, I'm going to write this down here. So X times the distributed load is equal to Q. So if I just bring these to where we can see them all. Which doesn't look like I can. So anyway, I have X is equal to Q over W, which is equal to 764.7 over 100 pounds, which is my reaction, divided by 100 pounds per foot, which is my line load. Feet comes to the top, and I have an X of, so 7.647 feet. Okay, so that's an important little piece of data that I want to use. Okay, so that tells me my moment is a maximum right here along this line. That's because my shear is positive here and my shear is negative here. So the shear here is going to be building up moment, and then the shear here is going to be taking it down. Now in my moment diagram, because I'm pinned at the ends, I have zero moment at the end. So I know here I'm zero, here I'm zero, here I'm a maximum, and then I decrease back to it. So the shape of the moment curve from here to here, because this is triangular, this is parabolic. So I'm just going to draw it in. You might ask, how do I know if I draw a line like that or a line like this? You can look at the magnitude of the shape. So here, because there's more shear, the rate of change of this line is going to be greater. So it's going to get bigger faster because this is big early. That's kind of conceptually how I think about it. Okay, so let's find this first point here. It's basically the area of the shear curve. So I have 765 pounds as the vertical portion of my triangle, times X of 7.65 divided by 2, because I only have half of it. So let's call this point X. My moment at X is equal to 765 pounds times 7.65 feet. So I'm just going to crank that out. I have the first part already, times 765. That's interesting. The numbers are very similar. So I have 50 pound feet. So 765, 765, 58, okay. Alright, so that's my moment at X. Now I need to decrease from this point to this point a certain amount. Now this time I'm decreasing slower at first and then faster, so it's going to look like this. And then I have a rectangular portion, so that's actually going to give me a straight line of moment. And then actually that slope's going to be a little less aggressive. And then at the end, so that's sloping down and that slopes all the way down. So this point is a little more than that point. Okay, let's go ahead and calculate at these 2 points. I'll call this A and B, and then we'll do one at the end. So I'm going to get an extra sheet of paper here, and hopefully we can see all of this at once. Okay, so the moment at point A is going to be the moment at X minus that area. So I have 5850 pound-feet minus that dimension. So if I back up to here, because that's 10 feet, that dimension is 10 minus that. So I have 10 minus 7.65, I'm just going to round a bit, times the magnitude of 235 pounds. That'll give me my moment at A. So I just throw that into the calculating machine. I have 5290, we'll call it 8 pound-feet, which is not a ton less, but somewhat less. So I'm just going to write that to 98 right there. Okay, so now the moment at B, I'm going to take this moment and subtract the area of that curve. So 5298 minus, let's see, 235 pounds. And then my length of this portion is 5 feet. So 235 times 5, subtract that, is 4123 pound-feet. And you can be more rigorous about your decimal places. In the end, it won't change anything that matters. Okay, so let's see if we can close this out. So I need to calc the area under that curve. So let's just say moment at Q is at S. So moment at S at the end. So I'm going to take 4123 minus the area of this curve. So I have 2 foot width and a certain height of 735. So 735 pounds, 2 feet. Dang it, that's not going to cancel out. So again, I've done something wrong. I'll need to go figure that out. Okay, well hopefully, well not hopefully, but that was fairly clear what I did wrong. I should have seen that, but I didn't. So the area under this curve is not 765 times 7.65. It's that divided by 2 because I have a triangle. So this number is half that value. 5850 divided by 2 is 2925. And I'm going to keep cleaning that up. So here, I need to erase that guy. And that guy. And I could redo this or edit it out, but the reality, this is how this goes sometimes. Oh, I have another mistake here because this area should be divided by 2 as well. Good thing I'm checking this. Too bad I didn't do it right the first time. Okay, so I have 2925, 10 minus 7.65 times 235 divided by 2, subtract gives me 2648. Let me just double check that. $26.48. Okay. So that answer is going to be different. That input will be different. That will be different. I guess I have maybe more practice at this than I care to admit. Okay, so the next part from A to B, just to make sure I have the full area, so width times height, so 235 times 5 feet. So 2648 minus 235 times 5 minus, I have 1474. That times 2 should get me pretty dang close. So 2 times 735 is 1470. I'm going to call that close enough to 0 because I'm not carrying a ton of decimal points. I could throw that in Excel and carry out as many as I wanted. And again, you can decide how you do that. Okay, bottom line is, in the end, when I do this first moment correctly, my magnitudes are correct. They're not written correctly here. I'm just going to erase them. And at the end of the day, my moment closes, which again is a check that I did it right. And so there's two ways to know if you do it right. One is to do your calcs right and check them and make sure you're correct. And a lot of times in our calcs we don't have a check, so we have to do that. Another way is just to close. If I can close my moment diagram or close my shear diagram, I know I'm correct because there's no other option but to be correct when they close. Alright, so this example runs through a combined distributed and point load. Sometimes you'll have a point load on a distributed load, and that just becomes a little more tedious. What you do in that case is just break up the distributed load on both sides of the point load. Alright, I think this gives you enough pain and suffering for your next assignment, so good luck with it. Hopefully this helps, and get in touch if you have troubles.